actually clipping it.
Yeah, yeah, yeah. Let's just hold it. Where's present?
Let me see this.
Yeah.
Okay.
Ready?
All right. Yeah. Let's get started.
All right, everyone. Let's get started. So today we're going to talk about attention networks. I know Professor Bishop put together a presentation over the break, which he streamed. I hope if you guys haven't gotten a chance to take a look at that, definitely look at it. We're going to present, a similar perspective, but hopefully it'll differ a little bit to give you some more some other details and a different insight. And we're also going to go over a more practical implementation to help you guys out on the next assignment.
Yeah. So I think it's a pretty different perspective from how Bishop explains attention. But like his, I believe, is more onto like the mathematical formulas and the whatnot. This one is more on the idea of why you even have attention in the first place. Yeah. And so first of all, let's talk about what kind of tasks use attention. So like typically if you look in the literature, you see when they do like a machine translation, they often have some kind of attention mechanism in there somewhere. And sometimes there's like image captioning tasks where given an image, you use attention somehow to create a caption that describes the image, and those get eerily really similar to how a person might write the caption, even though sometimes they mention like sails as skateboards or something. And then there's another one which I've been doing recently, which was given a document in question, both in natural language, it'll create an answer generatively using those two that like uses the document to answer that question. Again, it uses attention in there somewhere. Is anyone familiar with the squad task? Some machine comprehension. The best models right now also use attention for that. And so like attention seems to be very useful for these kinds of tasks, but what's special about those? Now let's go back to questions that recurrent networks are used in general. And specifically, let's look at this last one that I've mentioned, the idea of a generative architecture. Because if you think about it, the previous three were all had something to do with generation. And so there's this prior belief that like we have to see the entire sequence of the input before we can actually say anything about the output. Like to even create the first word of a translation, we have to read the entire sentence. Or like at least we have to be able to attend to any arbitrary position in the sentence, not just the beginning. And so like there's this belief that we have to see the entire sequence or like see any position of that sequence.
Yeah, and then with attention revision, you can sort of think about it as if you're trying to generate some kind of caption, you're integrating visual information over time to produce some final output, such as a caption. And that path is determined by whatever attention algorithm that you choose to use.
And so, said more simply, we have this like, our output sequence must depend on both of these things. First, all the past states of the network, which is what the recurrent network should be able to handle on its own. And second, the entire inputs. And we also need to have the entire input sequence. So like that's the part where we need attention. In deep learning, when we say like something is conditioned on something, it usually just means like it's one of the inputs to the neural network, although there are like different ways to make it condition as well. Like you could change the hidden states or something. But typically we can like think of it as giving it as one of the inputs. But then like the idea of, so for the most simple architecture, what I called the one-to-one, the output, each output only depended on the input. So like, well, not only the one-to-one like non-recurrent architecture, to be more exact. For the same input, you always get the same output. So the output is only conditioned on the input, you can say. For the RNN, it also depends on all its past states. That's like why we have all the hidden states being streamed through the entire process, so that like an arbitrarily like distant event in the past can also affect the output of the RNN at some current time. For a CNN, what is it conditioned on? Just the window, the small number of inputs from in the left and the right, or in the neighborhood, not arbitrarily far away, but still you can think of that as like being conditioned on something. So like, I think I wrote this before the actual lecture, but you've already learned about variational autoencoders, where we also have like behavior that's conditioned on on a randomly generated number, which was the reparameterization trick that Bixia talked about. And so we need to have this kind of like encoding of the information that we're trying to condition on, because all of the past states, if you want the unaltered information of that, that's the entire sequence, a variable length thing, and it's pretty hard to deal with. And so like that's why we have the hidden states. It maintains this like fixed length vector that stores only what's meaningful about the past inputs. And so when you train the recurrent network, you're training it not only to produce the correct output sequence, I mean, you are training it to create the output sequence, but like in the process, through backpropagation, through like dependencies and whatnot, it uses the hidden state to best store the past information. And so like using that information, it's like suited to best perform the task. It's not doing like a general purpose encoding of the entire input. And so like there's this one thing that we can do to like perform surgery on this RNN, and now it has no outputs. What happens now? So we still have the hidden state, but now it's only an encoding of the input data. It doesn't have to like remember what it's outputted before or do other things related to a task to its hidden state. Instead, this encoding is just storing information about the entire input sequence. And so you may know that there is no output, so we can't really train this on its own. So like typically this sort of architecture could make sense if it's part of something else. So like we first use this to create an encoding of the input, and then we use that in some other network too. And then we train that we create an output, and we train that network through backpropagation. It goes back to this one and tweaks it to like create a good encoding. Does anyone have questions so far? Okay, and so when we have this like generative architecture, typically we also have this like output network that's recurrent, because like it's creating one word at a time. And so we want to pass this the encoding information to that output network. And there are several ways to do it. Some are more practical than others. Some over here are like no one would think of ever doing. This is just the only ones these are just some that I've got to mind at the time. So like we could say pass an encoding of the input sequence at all the time steps. This is probably like the simplest way to do it, because then it doesn't have to store the data into memory. It just has it available every time. Or we could just pass it the first time and give it zeros for the rest, which that will require the network to just use its memory to store what's necessary about the input sequence the whole time, but it's still a feasible technique. We could also, as I said, initialize the hidden vector directly using like the encoded input sequence. And I think Bixia has talked about techniques like these, where you require the hidden vector to have the same size in both the input and the output, like both the encoding and output and the decoding RNNs. But then even if they're not the same size, you could still use some kind of like feed-forward network or just a linear layer to adjust it to the right size, and then you can directly change the hidden state as well. So for simplicity, I'll be like talking about this first one, but in principle, I think all the other ones should give a similar, you should see something like the similar results should apply for all the others. Does anyone have a question? Okay. And so here is our first prototype of a network that does our generative task. So first we use the network with no outputs to create an encoding of the entire input, the encoding being the hidden state of that recurrent network. And then we use that vector and we pass it in as one of the inputs to the output network at each time step. That's the simple approach that I mentioned earlier. And then in principle, this means that every output in the sequence of outputs should be dependent on the entire input, because like we passed in an encoding of the entire input. And so yeah, this does our task, right? So there's a few problems. I remember there was this like statement, right? You can't put the meaning of an entire sentence into one vector or something along the lines of that. And so we're using just one vector to store the data of an entire sequence. One vector doesn't change in size, but sequences can change in size. And so if you have a very long sentence or a very long sequence or something like that, then you could, not only might the information not fit, it would also be really complicated to find ways to like fit the necessary information into this hidden vector. You can't just go like element number 1 is related to input number 1 or something, because then some of them will be unused and some of them will be like missing and whatnot. And so we could still find ways to deal with this if we just knew what parts of the input sequence were important and we could throw away everything else. Then hopefully the important bits are a fixed size vector. Like the important bits can fit inside that and we use it directly. But right now we're using the same encoding for all the time steps. So if we think about like a sentence that we want to translate, we first turn that entire sentence into a vector. And then we're using that vector for every output of the translated sentence, which means that encoding probably has to have meaning of the entire sentence. You can't like get rid of something. Otherwise, if it gets rid of something, the output network will have no idea how to get it back, and then we get something wrong. And so yeah, in this case, our encoding can't really just focus on something important. It has to like store some useful information about the entire sentence in that task. And you can imagine something similar for the other tasks that use attention. And so this is a problem, right?
1 second, I want to clarify that we're actually streaming. Oh, no, we are. Okay.
Okay. Do you want to like open the slide on, open the stream on the other computer?
Oh yeah.
Okay. And so let's think of a second prototype where we want to create a vector that's different for every time step. So that like the idea we want is having one encoding for time step number 1, a different encoding for time step number 2, and so on. And where all of these encodings technically depend on the entire input sequence, but only contain like information that's useful for that one time step. And so an idea of how to do this is first, given the hidden state of an output network, we can give it to the input network so the input network knows what it needs to focus on, essentially. And then using our simple method of passing it at every time step, we condition the entire input network on the hidden state of the output network, and we get the encoding of the sequence, which depends on what the output network wanted at that time. And then we do this over and over. We get a new hidden state, and then we use that new hidden state to create a new encoding of the input. And we pass that back in, and we create a new output, and so on. And now this should actually focus on what's important on the input sequence at every time step. This is actually one of the more complicated architectures one of the more complicated prototypes that I brought up in this presentation. Does anyone have questions about this? Yeah?
So hidden state of x0 is different from hidden state of x1, right?
So like the rectangles over here are independent of like the x0s and x1s. They're just like a second input. But yeah, the hidden state behind x0 is the same as the one behind x1.
Well, what is the blue box on the top graph?
So I call this the hidden state of the output network at that time.
Top.
Yeah, so it gets this one is the same as that.
So why they're all same?
It's just one of the ways of making the network depend on this value. So there are many ways to do it. Like we could just pass it in once, or we could set the hidden state of the encoding network directly.
So we keep the blue box, and then we've got the orange one, and then we change the blue to a darker blue, and then
Yes.
get the darker orange.
Yeah, that's the idea.
Okay, thanks.
Does that make sense? All right.
What is the green? Is the orange one every time? The orange X.
Yeah, it's the idea is we want a different encoding of the input sequence at every time step.
Is it a hidden state of the previous output?
It's the hidden state at the last time step of the input network. So like we get the input network, we pass in all the inputs, and we get the final hidden state. and we pass that directly to the output network as like an encoding of the entire input sequence. Yeah.
But you're basically doing a whole run through the input sequence each time. Each time step in the decoding network, you're making a full pass through all time steps of the input sequence. So basically, it's, instead of saying we're going to one-off just make a single encoding and give it to the decoding network, at each step, we're now creating a new vector that's also dependent on the previous hidden state. So maybe we now need new information. Oh, let's go back to the input and see if we can pull that out. And then maybe now we need something else. We can go back and do a fresh pass instead of having to do a single encoding and then relying on that for the whole series of the decoding.
Yeah.
So that orange will change.
Is the final hidden state of the encoding. Yeah, but we go through the input sequence several times, so we have like many final hidden states.
Yeah, so it's confusing because we're only showing this for one time, just for here, but then we'll run through that again to get this.
Yeah.
And so these are passed, and these take over what those blue boxes are.
How is it supposed to be different when you run it multiple times?
So that's why we passed in the.
Feeding in the final hidden.
Yeah, so we have a different blue box every time we do it.
So orange box is the next time of blue box.
Is the what?
So you produce a orange box which you describe as the hidden state, new hidden state.
I'm just going to appreciate right now the level of our conversation talking about blue boxes. I think that's our fault. But, sorry. Yeah, sorry.
I can give a like specific example in terms of machine translation if you want. Although like there's no guarantee that the network actually does this. But suppose that we're given a sentence in one language. And so let's say this blue box is a hidden state saying, I want information about like people. Then we pass in this vector saying, I want people to the encoding network. And so it passes through the entire sequence and it looks for mentions of people. And it creates this like final vector, the orange box, which is like information about all the people in that sentence. And then that gets passed into the output sequence and it translates that person into a different word. And now it says like, I want verbs. And so it gets a new blue box, which basically encodes the meaning of I want verbs. And so the idea of I want verbs is passed into the the encoding sequence network. And then that creates a new vector saying information about verbs and so on.
So
Yeah.
information is passed back to the encoder.
Yeah, that's the idea. The idea of like,
It's a bidirectional information transfer. Right?
yeah, pretty much. It's like, it goes through time though, it's much like an actual recurrent network doesn't do it within a single time, but like it goes back to its recurrence across the time steps.
What's the relationship between this and attention?
So like this is kind of the most complicated way to do attention, that's what I'd say. So attention is like a more simplified way that reduces computation and like also is more practical and so on.
If I'm not wrong, I think attention just combine the different time steps features together to make a bigger vector.
We're just sort of building up to the motivation for the what you're describing is sort of the implementation of soft attention.
Yeah.
So we're going to get to that, but we're just kind of describing some ways in which someone can formulate a strategy for taking on this problem.
So yeah, this is like basically the least like general way. This is the most general way to do it. It's like the most complicated approach.
Yeah. So basically, to you guys, like the colors themselves are a little bit confusing, but it would make more sense if we had copied this top diagram of the encoder network with the different colors that we've labeled for the input hidden states. Inputs for the decoder.
Okay, yeah. So now let's talk about this prototype. So we do have like a different encoding at each time step. It's still lossy because like we use a single vector for the entire sequence. But now we can focus on what's important at every time step. So like the decoder says this, I want to focus on this information, and then the encoder creates an encoding that focuses on that information, and so on. But then like now our network is really complicated and hairy, and it also takes a very long time to run because we go through the entire sequence many, many times just to create like one output sequence. It's very computationally expensive. What can we do about this? And so there's this idea that like we probably don't need information about the entire input sequence. Like we already established that we can focus on certain things, or like we don't need the information about the entire sequence, though it could be anywhere. But is it enough if we just like have a single element of the input passed in at each time step? We're gonna like go over the idea of whether this actually works for later, but now let's suppose that for this task it actually works. Like maybe we don't, or maybe we're doing machine translation and we just need a word. Yeah.
Single element at random or with some verbal knowledge?
It's not at random. We're actually going to choose which element we want, and we'll be getting over how that works. And so, how do we choose which one we want? First of all, we can have an idea of having a key to each element of the input sequence, and then for example, if we have input 1, input 2, input 3 as our sequence, we can just give it a key. In this case, I just call it 1, 2, and 3, and so on. And then at each time step, we create like what we call a query, which says which key do I want to grab. This query is in principle like a vector, which is not just some like discrete number. We're using numbers to describe them here, but it's really the 1, 2s, and 3s are like vectors. And then the query is another vector, which might not actually be one of the existing keys.
The people on the stream are only getting a small part. I feel bad.
Wait, really?
I missed out. Yeah, I did too. Sorry, guys.
If you're watching this in the future,
Nothing like feedback.
you may want to like pull up the slides. They're available on Piazza too.
Yeah,
for the early part.
Our apologies. All right, I hope this is better.
Let's see. Does this show better? How's the stream? It takes like 10 seconds for it to.
Let me go live.
The title is still not showing. Oh, wait.
This is just the bottom.
Oh, only the bottom. I think I'm going through this more quickly then. Do we have like a prototype for recitation streaming?
Prototype?
Like everything already preset.
We should probably do that. We're going to admit our sins in the stream.
Okay. This like 10-second delay. Yeah, that looks good.
We're good.
Okay. So like we have our input sequence, which I'm denoting input 1, input 2, input 3, so on. And we have a key to each one. I'm calling this 1, 2, and 3, but they're not. They're actually going to be like vectors with some real numbers inside. And so like we use this like query, which denotes which key we want. In principle, this query is another vector, which might not actually be one of the ones in the sequence. So we generate this query, and we pick the one that's like most similar. Like we pick the key that is most similar to that query, and then we pick the value that's associated with that key, and we pass that in. This is like kind of an idea of how someone might do it if they don't they never actually checked how other people did attention and so on. Which this one's, it seems reasonable. We're creating the key, we're creating a query, we find the one most similar, and so on. There's many ways to compute similarity. We can use like dot product, cosine similarity. We can have a feed-forward network specifically for that purpose, so on. And we'll have questions about this one. Okay, no, I guess not. And so this is kind of like a very rudimentary hard attention mechanism. Yeah, we're actually getting to attention now. And so like instead of doing an encoding at each, using like our recurrent network and at each time step, which could be very expensive, we just we compute what we call an attention from the query to the inputs. The attention, computing attention is basically like finding the similarity between the query and the key for all the values. So in the end, we get like this similarity value for each value, like for each element in the input sequence. And that's like the process of computing an attention. Then from the like attention, which is the similarity values at each element in the sequence, we pick the one that's most similar. We can also do things probabilistically, like we can add gumball noise and then like choose it probabilistically and so on. So there's the pros over here is that we don't actually need to train an encoder. We know that the vectors that we pass in from the input sequence are already like meaningful on their own. That's why we have them as inputs. We don't have to like combine information about multiple things and like encode that and so on. But the thing is, as stated right here, this is not differentiable. Like if we change the query a little bit, we don't change what element we add to the attention mechanism at all. It's not like a differentiable mechanism. It's all completely discrete. Either this one's the most similar or that one's the most similar. There's no like middle ground. And also like if we do this wrong, we could also end up with just having like not enough information being passed in. So instead of an input sequence, we might have like an image. It's still everything I said before still applies perfectly. We just like we compute an attention from the query to each pixel of the image, pick the pixel that's most similar and put that in. But then a single pixel might not have all that much information, or it could be very noisy if like the image is not exactly perfectly continuous and smooth and so on. And so there could be some issues just picking like a single element as your input. Does anyone have, I think at this point maybe some people already have an idea of what soft attention is. So you can see like how soft attention is gonna fix these. Or rather like soft attention fixes these because like we haven't thought of ways to deal with the differentiability issue of hard attention. Ryan would actually be talking about a way we can actually still save it and use hard attention to address both problems. And so soft attention is like the easier way out. So instead of just like picking one element and like committing to that one, we can compute this like we first compute the similarity the same way, but then we somehow combine the information about the entire input sequence or image or whatever into like a single vector using this. And that's why we call it like soft. We don't commit to one of them. We basically choose all of them, or at least all of the ones that had a high similarity score. So like to be specific, one of the ways to do it is we first compute the similarity scores, then we do a softmax on that. And that will give us a probability distribution over the entire input sequence. And now we can basically do this weighted average using that probability distribution. So like if one input has a very high like if the softmax gives a value close to 1 for one of the inputs, then the resulting like fused attention vector, what we call it, will be very similar to the one element that had a high attention score. We use for example here, we have a dot product of the attention values being what we get out of the softmax, with the probability distribution. We find the dot product of that with the input sequence, and that gives us the weighted average that we need to pass into the network. Is everyone clear about how this works? We'll have like a kind of rudimentary diagram, but I don't think it's yeah.
Why this will work?
Why will this like work as you expect? Is it the idea that like maybe a weighted average is kind of a weird piece of information to pass in, or were you thinking of something else?
What do you call that query?
The query?
Yeah.
Oh, so we want to go back to this. So I guess query is somewhat of a overloaded term. We're using it here to describe the value that the output network creates at each time step, which determines which values of the input should be used. So like the query over here is these things. As I've shown it over here, it's like the first one is sort of a 2, and so we get, as a result, the second input is passed in. The next one is sort of an 8, and so as a result, the next one, the 8th input is passed in, and so on. And so You're saying why this works?
Yeah.
So like, why does this do what we expect it to do, or what?
Yeah, where this method maps what we want to like implement the attention.
Okay, so basically,
Well, so I mean, I guess before what we're talking about is the problem is like, how do we, give the decoder useful information at a specific time step, and we need to select that from information, useful information.
How to define useful information.
Well, that's not exactly what we're doing here. We're saying that we have it. How do we assign it?
so the network will like train itself so that it gives the right query, so that it finds useful information.
Just a confusing.
That doesn't make sense in this case where we're actually having like hard keys and like discrete queries. As I said before, you can't differentiate that. But like when we actually put it into this form where we're doing like a softer like similarity score as sort of a lookup, and then we use that actually to weight. We're not like doing a lookup and like selecting an input to for a certain time step. We're now going to do a weighting across inputs.
Narrative score. What can you do with that?
We're making an analogy. Well, we're going to talk about that. That's what the attention is, and that will tell us how we weight or consider the inputs at a given time step.
So like, if you remember the machine translation example I gave before with like the complicated example, we said we encode the entire input to have information about people, and then we encode the entire input to have information about verbs. In this attention example, we can just say the query is people, and then it finds which input of the sequence is like has a key that that says it's a person. And so by the hard attention mechanism, a person-related word would just come in directly into the network instead of having to do an encoding of the entire thing. So, and then like next one, it says, give me a verb. And then the query would be basically saying something about needing a verb. And then it would find the key that is most similar to that query. So it finds a verb. And then that gets passed in directly to the output sequence. Output network, I mean. Does that example make sense? Or so it's basically a much harder version of the previous idea. We're just picking exactly one input element.
Okay.
And so, did we finish this one?
Did we?
Oh, yeah, we did.
Yep.
And so here's the rudimentary diagram. Or rather, this is an illustration of an idea. The next page is the diagram, I believe. Which is sometimes when we do this weighted average of inputs, we could get nonsense out of it. That was the whole idea of not having to use an encoding for the hard attention, because a single vector from the input is guaranteed to be meaningful if we don't do this kind of averaging thing. But if we do averaging of the inputs, we could get something weird. For example, over here, I picked some words that they're kind of like negative sounding words. So we can imagine doing some kind of sentiment analysis at that point in time. So we say like this restaurant is late, or it's costly, or something is annoying, or
The stream is broken.
yes. And so if we take like a weighted average of that, we just get blobs, not anything meaningful. So like we may have to create an encoding of the items to such that the weighted average still makes sense. Like if we say late is some kind of reddish color, annoying is some kind of anger, redder, even redder, sadly some kind of blue color. We can take the average and we get something that looks like that, which still could be meaningful. And so here's like a diagram of the soft attention mechanism. So first of all, we create the encoding of each element of the input sequence. We don't have to create an encoding of the entire sequence, just of each element. So we can just use like a simple like one-to-one network, or we can use convolution, or even recurrent if we wanted to. But basically, we just need one encoding for each input element. And then for each time step of the output, we compute the attention onto the sequence using the same idea of the queries and the keys. And then we do what we call a fusing, which is we compute the attention values, and we do the dot product, and we create a single vector out of that. Then we pass the fused vector to the output recurrent network. So this is how like soft attention works in general. Does anyone have questions about this?
So they colored boxes, dilated same way to that.
It's a fused vector, so like we have some kind of weighted average. For example, this one is a query that's kind of between a 2 and a 4. And so we kind of combine the 2 and the 4 somehow, and we get this. Then the next one is like sort of both an 8 and a 7. There's no 8 and 7 here, but let's suppose they did. We combine the we combine the encodings with the attention mechanism to get a fused vector. And then that gets passed in next.
Okay, so where is the bottom colored box come from?
So this is some combination of these.
Yeah.
What is where's the box come from?
The first one, there's many ways to like deal with it. We could just pick, like, we could have a initial vector, initial query or something, or we could just not pick anything, give it 0. It depends on the task, I guess. There's many ways to deal with the first one.
So, okay, now first step is we have first the box generated, and then do some combination so we can generate the next box. Or
Yeah, so we generate the combination using attention. So first we have this query, and then we compute the attention from the query to the input sequence. Computing attention means like calculating similarities and so on.
so now query is one of the white box, right?
Query is one of these, yeah.
One of these.
It's the outputs of the output network that relate to the keys of the input sequence. So like for a query and a key has like the same format, although a query might not be exactly one of the keys in the input sequence. They have like the same vector size and so on, and we should have similar interpretations.
Okay, will we see the code later?
Yeah, there will be code, yeah.
We're going to go over that code, yeah. But I mean, it's not going to be as like stripped down as this. Like,
Yeah,
you know, you're not going to see exactly.
it's like,
That's why
it doesn't visualize the
Yeah.
network's direct outputs like these.
That's sort of what you're saying is, right? So like, you know, we have a query here, but what it's saying is, you know, what information is going to be helpful at the next step. But in that information is now, you know, some convex combination of the inputs. And we're just using this query with the keys that we've defined to generate that distribution that we apply.
Yeah,
Can be verified.
so like when we compute the attention, we will get a variable length vector saying like how similar each input value is to the query. And then when we get the attention values by doing softmax, it'll still be variable because like we have a variable number of items, a distribution over those number of items. But finally, when we fuse the vector, it will no longer be variable. It's kind of like pooling that you've done in homework 2. It's like an average, except it's weighted.
Fuse is dot product.
Let's see, do I have it mentioned here?
Before?
It's the next one. Fusing is strictly for soft attention. And so like fusing, I guess I forgot to mention, is this process of computing the dot product with the attention values and the input sequence. And so if the input sequence has a variable size, that's still fine, because now we're basically taking an average, and now there's only one vector.
So the attention size is same as the input sequential size.
It's basically like the size of each element of the input sequence.
Oh,
It's-
sequence length, something like
It's no longer dependent on the sequence length, but it is dependent on like basically how many dimensions each value of the input sequence is. So like it's like number of channels vs the size of the image. Right now we no longer care about the size of the input. Instead we care about like the channels or the dimensionality of each.
So this means for each time step, this attention's channel set will be same as the input channel.
Yes.
Oh.
And so that's what we get this, we fuse the attentions and we get this kind of architecture. All right. And so there's some simplifications that people can do that will still work. So like often when people do attention, they don't like directly create a query, directly create keys, combine them like that. Instead, you often see that something weird, like people use the RNN state directly to like compute the attention directly onto the inputs. So at least for me, first time I saw that, I thought like this seems very non-rigorous. How can they actually do that? It makes no sense. So like the idea is you can have the query just be the hidden state of the output RNN, which sounds weird because the hidden state of the output RNN should already be occupied with doing something else. It's trying to create the values of each output element of the output sequence. So how come you can also use it to do something else? The keys can also just be the encoded input items directly, which also sounds weird because when you use it as a key, you're trying to find similarity. When you're using it as data, then it's data. It's not used for similarity. But this still can work because the network can learn. It can learn a way to like actually make it serve both purposes. So like for example over here, I've just created what I thought could be a reasonable approach to this. So we could say we use these last three elements of this, what's it, how many dimensions? 1, 2, 3, 4, 5, a 20-dimensional vector. Let's say we just use the last three of them purely for our like attention purposes, for similarity. So like we can think of those three numbers as like the key. And then right here, y could be like our query and also the hidden state of the RNN. And so all these like other values up to dimension 17 contain information that the RNN needs to create the output values. And then the last three play the role of a query so that you can compare it directly with the input sequences. So if we do the dot product of the query and the input, if we do the dot product, we still get 1, which is what we get something very close to 1, which is what we'd get if we directly had the dot product of the query and the key. But now this vector can still contain the other information that we needed. So I'm not saying that the network directly does this, but it can do something analogous such that even though the vector contains data that's needed for something else, it can make that data like play a very small role with the similarity metric. And so like if you take the dot product, it'll still be acting as if you had a key in a query.
Yeah, and I guess that would present some other interesting area of research to see if that's actually what's going on and how you can optimize that. But.
Yeah.
Because we typically over-parameterize the neural model in general. We just have a lot of redundant things that are there, like
Yeah.
doing something useful.
The network is always
In neural networks.
it's always over-parameterized.
Neural networks are always over-parameterized.
Yeah.
Usually,
Although the question is like whether we have enough like room to use this over-parameterization, because we do it for a reason. If we try to use too much of that free space, then the network will struggle to learn. And so, yeah, does anyone else have questions about this idea? So this is why in like the literature you don't see people say like we compute a query directly, we compute a key directly, we use that and then we do a lookup. Although sometimes they might. And so like here's a more mathematical approach to like the whole idea, which is suppose that we have an encoding function, just we call it just f encoder, which takes in the input sequence, what we call v, and we create an encoding that creates an encoding for each element. So first of all, if we had n input elements, and each one has k dimensions, then we encode it such that we still have n input elements, but maybe a different number of dimensions, like d. We can say that this is our hidden state. And then we also have our output RNN's hidden state at every time step, which is a d-dimensional vector. And first of all, we encode the input, we get the encoded values. We use softmax with, we first multiply by the output RNN's hidden state. This multiplication is computing the attention. Then we do softmax, which finds the attention values. And that gives us we get attention values. We do the dot product of our encoded input sequence with the attention values to get the fused vector. And then we create an output value from that using the hidden state and also that fused vector. So to iterate, this is CEH sub t computing the attention, softmax computes the attention values, and E transpose A sub t is fusing the vector. Does anyone have questions about this this mathematical approach?
Sorry, the E
Yeah.
transpose AT is the fuse.
Yeah, that's the fusing process. And this one is using the simplifications that I've mentioned in the previous slide, which is the query is the hidden state of the output RNN.
Yeah, it's a lot at first, but if you go through it step by step and see what you're doing at every step, and draw those usually those analogies of the query, although they can be confusing at first, will actually be helpful later on to understand what's going on.
And so there's been a paper that says like basically we can do everything with just attention. We don't even need recurrent networks. We don't need anything else. And it's actually pretty interesting. They get like very competitive results with it. And so the main idea is, first of all, you can do attention from one input element to the rest of the input elements. And that'll give you that'll basically be an encoding of the input element that is like kind of what we call context aware. It's instead of each input element be standing on its own, it's like somehow encoded in a way that depends on all the others. So if you think about it, when we use an RNN to encode something, we're giving it like awareness of its context. Same with a CNN. And if we do attention like this, we can also make an input element be like encoded in a way that's context aware. It basically just means its value depends on all the others. And we can also do something very similar to an output RNN using just attention. So first of all, we have an attention from a hidden state at one time step to the hidden state at all the previous time steps. And then like using that attention, we compute a value. And we do this over and over. If you think about it, this also conditions each value of the output to the previous values. It's like, on principle,
So, yeah, sorry, where was I? Markov reward process. Credit assignment, yeah. So a lot of the times we do something, we wait a certain number of time steps, we get a reward. How do we know what actions we took are actually beneficial for doing that reward? Was it the action that we took just before we got the reward, or was it, say 1,000 time steps ago? So we can use these algorithms to actually help us deal with hard attention, and we can now formulate where we attend to in our data is now actually a decision problem. So there's this really cool paper called Recurrent Models for Visual Attention, where they do this for basically image recognition, but they make it flexible enough such that you can perform a multitude of tasks. So what they do is they have this thing called the glimpse sensor, which is basically a noisy patch of the source image, and they have a policy network that takes the hidden state of the RNN, and it makes a decision of where to place the glimpse sensor next. So basically, what a policy is in the reinforcement learning formality is a probability distribution over actions conditioned on a certain state. And the reason that we can condition on a certain state is because it's a Markov process. We're making the independence assumption of previous states.
You want to summarize the overall idea of having like a glimpse sensor and moving it around?
Yeah, sure. So I guess the overall idea of in terms of what?
So like basically we're moving the glimpse sensor to acquire information.
Oh yeah. So instead of like in soft attention where we're waiting the whole input scene, we can now move this glimpse sensor around, and we not only just based on past information, but also directly focusing on the task, because now we have a set of rewards that we're trying to optimize to gain as we act. And not only that, so you can see here this F theta. This is the policy, which is telling us where to place the glimpse sensor next. But we also have another network which is doing a more general action, which is the actual objective of the task. So basically, in this one, it's scanning around this image, and it's making a prediction of what the image label is. But you can imagine that it could also be driving a car, or doing any other task. So as we drive too, we're not looking at the whole scene at once. We're looking at important parts, maybe just on the lines of the road. So this makes this very flexible, and they get really good results with this model. So you can see here. This? No, it's not. But yeah, so here's just a bigger overview of their setup with their glimpse sensor, which feeds into a network, and this is basically an RNN where at each time step we're selecting the next part of the source image to attend to. And then here's some results. So you can see that these are the glimpse paths. So these are showing the path of the location that the agent has decided at each time step. And then here, these sort of blurred out parts, we can see in focus what the network is looking at each time step. And you can kind of see here that it nicely went into sort of the shape of the 4 here to figure out that was a 4. But obviously, this is a very simple task, and it can be extended to other things. Okay, do you want to pull up the notebook?
Yeah, that's sure. So here's an example of a attention network. We wanted it to be simple, but then it turns out we sort of over-engineered it at the end. Turns out it's pretty hard to make demonstrations for attention networks.
Yeah.
If you don't really care and you just want to get a good accuracy, then it's not as bad.
Did you push it here?
Huh?
Did you push it to the
Yeah, it should be. Wait, oh, it's in Ben's repo though.
Oh, 1 sec. May have to.
sound? Yeah. Okay. No, homework 4 is
It's not about attention.
yeah, homework 4 is just an end-to-end network on phonemes. So I don't think we have explicit homework on attention, but I think some people's like projects could be related. And so like here is our very simple task, which what I call like a collared numbers task. I made this to basically like is a simpler version of an image captioning task, where given an image, you create a caption that describes it. So I just created an artificial data set where each image looks like this. It has 3 digits. And one of them is red, one of them is blue, and one of them is green. And so the caption will always have to look like this. First of all, you say what the red digit is, then you say what the green digit is, then you say what the blue digit is. So, and those 3 digits could be anywhere. Like the red 3 could have been on the right, and so on. So like an example caption for this is red 3 left, green 6 middle, blue 0 right. This is like a description of the entire thing. And so, I think you went past something. So first of all, we have a dictionary which only contains 16 distinct words, which is like 0 through 10, and then left, middle, right, red, green, blue. And then the caption will describe it like this: red 3 left, green 6 middle, blue 0 right. And basically what we do is we do a convolutional network onto the input image. This is our encoding step, where each pixel now has some kind of encoding to it. And then, like in this example, it's sort of, we have a separate keys and values. We use like 2 different convolutional networks at the end to do that. So I've tried to do it with a single, which in principle works, but like the demonstrations don't look as good. Like the pictures don't look very nice. And then we also have we compute a attention onto the input. And like this one is engineered in a way so that it computes multiple attentions. If you want, you can look into that. But for many real-world tasks, you only need 1. And then finally, like with softmax, it works. But then like softmax tends to give you kind of things similar to hard attention. So like even though it's soft, it could have like a lot of attention onto 1 pixel and so on. It's like sometimes a single pixel contains the information that you need already. And so, let's see, what was above? And then finally we have, a few explicit linear layers to convert the hidden state of the RNN to the values that we need at the output. So that I think is fairly typical, because the output over here is only a 16-dimensional vector, whereas we might want to have a high-dimensional hidden state, and so on. And so like this is just me loading the network. Here's like a description of what's inside of it. You can see the convolutional layers at the top, 2 separate convolutional layers for the key and the value in this case. And then we could have, I have an embedding to deal with the 16-dimensional vocabulary. We have several recurrent networks. And then we have several linear layers for the output and for the queries. Does anyone have questions about this idea? A lot of, oh, okay. Can you zoom into the? In this case, we have like several queries, but for many real-world tasks, we don't need that many. But like in principle, it's possible to compute several different attentions independently and then combine the information from that. This is just like me doing that to get a better demonstration pictures. And so now let's run the network on the example that we had above, and then we look at the attentions while we're doing it. So first of all, we run our network, and it did give us the value we want: red 3 left, green 6 middle, blue 0 right. But what did it do in the meanwhile? So first of all, this is the very first time step it computed in attention. You can see that it's highlighting the 0 and the 3 and the 6. So this is sort of strange, because like the first thing it should be looking at is the 3, while it's looking at everything. And so the very first value it's outputting is actually just red. And it's, no matter what input you get, it's always going to be the word red. And so the network learns really quickly that it just needs to say red at the very first word. And so what it does, what I think it's doing over here, I can't say whether or not that's actually what it's doing, is that it's using that one time step as an opportunity to get more information. So it's like it's looking at all the digits at the very beginning because it doesn't have to do anything else. And then now it's saying the red digit is. In this case, it was a 3. And so you should see attention onto the 3 in, I think it's the one immediately there, yeah. So now the 3 is being lit up really strongly. At the same time, it's also trying to get more information about 0 for some reason, which I can't claim directly why the network is doing that. But if you think about it, the recurrent network has a memory. And so it can like grab attention information and put it into memory and use it later. So it's possible that it's getting information about the 0 at this time step and using it when it needs to later. Or maybe it's just because like it has its hands free and it just doesn't really need to do anything, so it just chooses to attend to the 0 or something. But either way, the important bit is that it did attend to the 3, and that's how it knew that the 3 is the digit that it needed at that time. And now the next one was the 6, and now in this demonstration, it's really clear that it really wants information about the 6. So this point, technically at this time step, it's still saying like where the red digit is. It should be saying like left because the 3 was on the left and it was red. But like, since I guess in a sense it already had that information because like the network is sort of over-parameterized. So it's using this opportunity to get information about the next digit. So like the next digit it will be doing is the 6, the green 6 in the middle. And so now it would be spending a lot of attention onto the green 6 at that point. Either because like it wants to be extra sure about the 6 or it doesn't really have anything else to do or whatever. It's like paying attention to that 6 while it's saying like green 6 middle. And so you can see the 6 is lighting up. The 0 is being anti-lit up. And the 3 is sort of neutral. And so it doesn't really change for a while until it finally gets to the 0. Like once it's about to say where the green digit is, which is middle, I think at that point it starts to pay attention to the 0. And so, yeah, now it paid attention to the 0 and it's making extra sure to not pay attention to the 6 and the 3. And so now at this point it's saying like it's the 0 and it's blue and it's on the right and so on. And I think it doesn't really change past that point. So a lot of the specific behavior of this network is just a quirk of this specific network. It's if you train this several times, you get very different quirks. This one happened to like get information about all the digits on the first time step, and it procrastinated for the red digit until the very end. But sometime, like a previous time when I run it, it actually procrastinated on the blue digit, and it like spent a lot of attention on the red one for some reason, even though it's no longer relevant. So like you get a lot of different quirks, but in the end it works out. So this demo is actually sort of hard to make because it turns out for this simple tasks, even if your convolutional network is complicated enough, it could just store the information it needs directly. It could say like the first 10 channels will be information about the red digit, the next 10 channels will be information about the blue digit, and so on. And so even if you just average the entire image, it could still like do well on this task. And similarly for a very complex RNN, it could be doing lots of really weird things with memory, like it could attend to all of the digits at the same time and then put that all into memory, and then for the rest of the time steps, nothing interesting happens. And so like I had to basically specifically cripple both the RNN and the CNN so that this like demo would work. But if you think about it, for a real world task, the image will be complicated, and you can't get away with just a really complicated RNN or a really complicated CNN to store information about the entire thing at once. And so though the CNN and RNN is relatively small in this task, it would guaranteed be too small for like a bigger image captioning task. And so I guess the crippling it is just to simulate that effect. Does anyone have questions about the demo? Yeah, I could show the code, but it is sort of like uncommented in.
Yeah, but like we're gonna make this all available
Yeah.
So. Okay. Yeah. Are there any other questions about attention? Okay. No? All right. I think we're all set.
Yeah, I think that's it.
Thank you guys.